All right, like you know it. I think it's working. Miraculous. All right, guys. I wanted to just maybe go over one or two more of these graphs, and then I want to move on to the holes and the even odd function stuff. So, well, we'll make some class time to just kind of work through the rest as well. But again, yeah, this being an AP class with the volume of material we got to get through, there is you do have to do a bit outside of class to keep up with the material. So just keep that in mind. So hopefully you got a few of these graphs done. If you got 3 or 4 of them done, then you're doing good. I just wanted to maybe briefly look at maybe like 10 and 11. Does anyone have 10 done that wants to just come up and do it for me? Anyone out there? Oh, George?
So I cannot say that I have it done.
Thanks for sharing that, George.
I have it done, but well, yeah.
I feel like
I'll come up if you want me to.
it doesn't sound that keen on doing it, so that's
Okay.
no pressure. All right, so this is, I mean, my goal, what I would like for you guys is when you see a function like this, especially down the road when it's like, we got to do some calculus with this function. I'd hope that you can look at this and get some general sense, not like a perfect picture in your head of what it looks like, but be able to look at that and go, well, I know some of its properties. Like, hopefully you can look at that and go, well, there's 2 asymptotes, there's 2 vertical asymptotes, there's a horizontal asymptote, so I know what's happening on the far left and the far right. So, something's happening at -2, a 0. There's a special kind of 0 at -2. Does anyone know the answer to that?
Bouncy boy.
Bouncy, yeah, it's a root of multiplicity 2, but I like to say they're bouncy. It's going to bounce off the x-axis at -2. Okay, now why is that? Because that root's getting squared. Okay, the term that's generating the 0 is squared. So if you think about being on either side of -2, say -2.1 versus -1.9, they're going to produce the exact same, they'd both be positive in this case. Because the top's going to be positive because of the square, and the bottom, say plug in -2.1, it's positive. So anyway, so getting into it here, what this looks like, you have the 2 vertical asymptotes. There's one x equals 1. There's another one x equals -1. And then the root is at -2, 0. What's one more piece of info we could put on the graph? Oh yeah. The other intercept, which is what?
That's 0, -4.
No, it's not 0. It's 1.
I was like, wow.
Wait.
Yeah, thank you. The y-intercept is -4.
Yeah.
Everyone okay with that?
Yeah.
So this is where it gets a little tricky, is how do you get everything to fit inside the graph? Well, you can't, let's maybe do the middle section first. I usually find the middles kind of the easiest to think about. Maybe it just depends on the function. But and all I'm saying here is I can't cross this x-axis, right? So I can't do something like this, something like that. It's got to be kind of contained down here. Now I don't know that like say the peak of this Humpty Dumpty here is at 0, -4. It could very well. I mean, it's likely that it happens somewhere else, but I'm not that concerned. All I know is that this graph should be contained below the x-axis between these 2 vertical asymptotes. So everyone okay with that first part?
Mm-hmm.
So now, what else? Well, there needs to be a right side of the graph. Well, the graph can't do this. I know it's got to approach this asymptote, and it's got to approach this asymptote, but it can't do this because that would require crossing the x-axis, but we've already enumerated all the x-intercepts, so it's got to be this. Like that. And then the more interesting structure on this, I think, is the left side, because you might be tempted to do this, but like I said earlier, if you plug in any number less than -1 into this. And hopefully it's obvious. The top is guaranteed to be non-negative because of the square. And the bottom, if x was -1.1, then the bottom is positive. So really all these numbers here are positive. So the graph has to bounce. That's the bounce I was talking about. So when you see, when you see a graph like this and you think hard about where did its shape come from, what parts of the equation generated each part? Well, this little square here generates this sort of bouncing behavior. Okay? So let's compare that to number 11. Don't shout it out if you know it. I want everyone to think about this one. So this graph has a big fundamental difference from every graph before it. Every graph from 1 through 10 has a certain thing going on that this graph does not have. So think about that for a second. What really sets this graph apart from all the other ones so far? Yeah, so it's, what'd you say, Alyssa? It has, and then, is that Aaron?
Yeah.
Those are almost equivalent statements, right?
Yeah.
So I say almost equivalent, because in this context, they're pretty much equivalent. But as in this one, domain's all real, so the bottom of this fraction can never equal 0, right? So the domain's all reals, which means then there can't be any vertical asymptotes. Okay, so but what else do we know? How about horizontal asymptotes on this?
Yeah.
Yeah, so the end behavior on this is as x approaches infinity, y approaches 0. Same thing for negative infinity. That's the case. So these are the horizontal asymptote of y equals 0. So I probably again, don't make the mistake of thinking that you can't cross a horizontal asymptote. You certainly can. This one's going to cross at 0 or 2, 0. 2, 0. Very good. So now, what's maybe one more piece of info we can put on the graph before we start drawing it?
Y-intercept.
The y-intercept, which is at
0, 2.
Okay, so we have these 2 points. We have the end behavior. Okay. One more thing you might want to think about is maybe if x is bigger than 2, all the y values are, what do you guys think? So complete the statement in your mind. If x is any number bigger than 2, the y value must be negative. So all these y values over here are negative. Likewise, if x is less than 2, then y has to be positive. So everything on the left of 2 is positive, everything on the right of 2 is negative. So with all that together, I mean, it's fair. I'd say it's probably kind of straightforward what it looks like. As far as kind of a weird shape, right? But we just know that it has to, this is forced to happen. This must happen. These 2 points must happen. So there's no other real way for it to really fit onto the graph. Again, if you punch this into Desmos, it might look a little different. A lot of times they're really flat here. So sometimes, when we're drawing it freehand, we might exaggerate the size of the humps. So one thing we'll do in this class is we'll show basically how could you find like the minimum, like what x and y value is that? Because logically there must be some bottom to that curve, right? There must be a lowest point since it dips down below 0 and then approaches 0, and then we'll apply some calculus to. That's one of the many things that calculus does, is it finds these minimum and maximum points. All right, before we move on, any questions, guys? Stumping you? Okay, sweet. All right.
I have one thing.
What?
How can we assume that Humpty Dumpty is an
That he's an egg?
egg? Mm-hmm.
That's a good question. Yeah, because it's never explicitly said. Why? How does he fall off a wall and break?
How'd he get on there?
But like, couldn't it be like? Couldn't Humpty Dumpty be anything that can break, not an egg?
True. It could be a vase.
Yeah.
That's how you say vase if you're really skinny.
Bougie.
You say
Yeah.
vase.
Yes.
Thank you,
I like that.
You're welcome.
It's good stuff there.
Thank you. I try.
Okay. Reminds me, I don't know why it reminds me, but it reminds me of like Rudolph the Red-Nosed Reindeer. I think it's like the most horrible story.
Yeah,
It is.
They're like so
Terrible.
mean to him, and then all of a sudden, oh well, you're useful to us. We can use your red nose. And then he's like, okay. He should be like, no, I'm gonna go start my own North Pole.
Yeah, exactly.
Like, screw you
You
guys.
know about the social gratification.
Well, yeah, it's like all the messages like, if all like the mean kids are like finally they are nice to you because they whatever want to come use your pool or something, then yes, you've made it. Finally, they
Yeah.
accepted you. Like, no, I don't know.
But then you
Yeah,
get burned
it's
again.
terrible.
Yeah.
And you learn your lesson.
It's terrible. Or
Because
it's
you have to
like,
have it.
it's like The Little Mermaid.
Yeah, Little Mermaid's bad too.
That one I can't really remember what happens. I know
Well,
there's
it's
like
like-
there's like
it's
a
like-
crab in it, isn't there?
That's the only part that needs to be done.
Yeah, I mean, it's
crab.
basically just like give up everything you know and you're like the one thing that you cherish to be with the guy you met once.
I'll have to watch. I really cannot remember a single part of the
That's
Well, are you
fine.
I
talking
know there's a
about
mermaid.
original?
That's literally all I can
or-
remember.
No,
And
the
there's a crab.
original is good.
The
The
original's
original
good.
Little Mermaid.
Well, I mean, I wouldn't say it's
sad.
good. It's very depressing.
Yeah,
but
but it's good message. The new
The
Little
morals are
Mermaid
better.
bad message, but
I'll have to rewatch it.
more kid friendly than the original.
Okay, so I grouped these ones together this time. I can't remember. Maybe last year I'd already edited them. In the years past, I had all the whole ones were kind of lumped in with the other ones, and I just found it produced a lot of confusion. So I'm not sure for you guys who took it last year if they were split up yet. But anyway, so there's a function. Now you might be looking at that and going, "This one's kind of weird because if x was 1, what would y be?"
Zero.
No, undefined.
It would be 0 divided by 0. What's 0 divided by 0?
Undefined.
One?
It's an interesting question. It is okay. If you just ask the question straight, in a vacuum of what is 0 divided by 0, the answer is undefined. That's the most safe answer. But in this case, it's kind of like 1/2 is actually kind of like the answer.
Yeah.
1/2 is 0. What's 0 divided by 0? 1/2. So, and I'll show you why that is the case.
It's one over.
Very good. So Trey's a step ahead of us here. So that's good. Yeah. So so what I'm trying to show you here is when you're dealing with this thing here, and you go, hey, domain, x can't be 1 or -1. And then you go, but wait a second. One of those, the 1, would produce a 0 over 0 form. So if you get 0 over 0, you want to look for holes. Okay, that kind of thing tends to generate holes in graphs. Okay, so what Trey said was, we'll look for some kind of factorization. So if we factor the bottom into x minus 1 times x plus 1, make sure you know that one. Difference of squares comes up a lot. You notice, oh, wait a second, those cancel out. Sorry. What I'm going to do, this is technically wrong. That is wrong. If you're taking an AP exam and you wrote that, you would just lose the points because that's not correct. That is not a valid use of this symbol here. Okay, so what you need to do is go y equals 1 over x plus 1 with a caveat that x can't be 1. Now they're the same. Okay? Because that thing I wrote there if I write this, let me just elaborate there real quick. Why is that wrong? Well, this is an expression that one can be plugged into. This is not. So they're not the same. They're not the same thing. They're not equal. So this is the same. So now what you do, and again, just real quick here, what's happening here is x still can't be 1. You still can't plug in 1, but you could plug in 0.999, right? Now, if you were to plug in 0.999 into this, what it would look like would be 0.999 minus 1 over 0.999 minus 1 times 0.999 plus 1. Now that number's not 0, but they can still cancel out. And look what your answer is. Awfully close to, awfully close to, well, 1 over x plus 1, where x is 0.9. So the point here, the reason you can factor it out is because you're saying that x can't be 1. So if you were wondering. Long story short, if it's the same factors on top and bottom, you can pretty much, say I'm canceling them, and then saying that x can't be that. So anyway, what does that graph look like? And that's an easy one. Hopefully it's this function. It's the 1 over x function, shifted left 1. So you draw that. This is where having a marker is nice. If the pencil is a little more of a pain, because I can just draw it and then go, oh yeah, when x is 1, there's a hole there. So that's what I meant earlier when I said that in this particular context, 0 divided by 0 is kind of like 1/2. And what I meant by that in like precise terms is that the limit of this function as x approaches 1 from both sides is 1/2. Now, how do I get the 1/2? How do I know that y value is 1/2? Well, you simply plug the 1 in. You say, oh, it says you can't plug 1 in, but you go, well, I could. Technically, you're going, well, if I plugged in 0.99999 and plugged in 1.00001, then both of those would converge and be very close to 1/2 on both sides. But in practice, all you do is you take your forbidden value and you plug it in.
Forbidden value.
It is. That's why it's forbidden. It is. It's not allowed. It's not allowed. Glad you like that, Jesse. Okay, so.
Oh, sorry. I'm sorry. I didn't mean to. I tried to cross my legs and it was disastrous.
Okay, so let's skip. So you're gonna find that part B is very, very similar to this. They're very close to each other. Okay. I want to just briefly go over C. C is one you might possibly remember from last year. I don't know. Maybe all of them. I kind of remember all of them. Or how about this? You guys do C real quick. Shouldn't take you more than a minute or two. Look for factorization, try to figure it out, and then we'll go over the answer real quick. You like this one better? You don't, just to clarify, you do not need to list out all the stuff from before. All you need to do is find out the coordinates of the hole. So in this case, the hole was at, make sure you get both coordinates, x value and y value. So there's how you say the answer. And then you draw a rough sketch. And then obviously you want to write the reduced form of the equation. I wonder if this will look better if I put this computer up on like a little pedestal. That might look better. Jesse, is that harder for you to see? If I do that?
No. I mean, if you write all the way down there, but I can just do this. I'm not, it's fine. It's, any, okay. Well, now you're blocking context. That's fine. Okay, Jesus, sure.
I gotta move it. Okay, so was that enough time? You should have got, if you factored that correctly, you should have got x minus 3, where x can't be negative 3, which means it's a straight line. And the y value associated with the whole, in this case, would be negative 6. Are there any questions on the solution there? Does that make sense?
I have a question, just because for some reason I was thinking there's a vertical asymptote at -3 and a whole at +3.
Well, so the thought process is you start with this, you say,
It's x +3.
oh, okay, so when you look at that, you first go, this is where it's tricky, you say, I totally understand why someone would look at this and go, oh, vertical asymptote at -3. The problem though is a vertical asymptote isn't generated automatically if the bottom of the fraction is 0. What makes a vertical asymptote is when you have something going on where, like, for example, say you had x over x plus 3. This one's a vertical asymptote. So if you plug in -3, or let's say I plug in -2.999. The top would be -2.999. The bottom would be very small, and then that would produce, so what that would do is that would produce a y value of -2,999. That's where those gigantic y values are coming from on a vertical asymptote. Whereas this one, they do the same thing. If I plug in, let me factor the top. If I plug in -2.999 in here, this would be 0.001. This would be -5.999, and this would be 0.001 again. Notice those cancel out, and I get a y value awfully close to -6.
Okay.
So long story short is if the number that makes the bottom 0 also makes the top 0, then you're probably looking at a hole. Most likely. There's a couple in here where after you're done, at least I think there are, after you factor out, there's still the asymptote there. So maybe we can find one of those after we do this one. Okay, is everyone okay with that? Does that make sense? This one's kind of weird. Take a second, look at that. Try to. This is the last one on number 14.
Okay.
There's 2 pages of whole
I needed
questions.
the 14 part. Gotcha.
The hint here, if you're stuck at all, is there's a sneaky factorization.
Yeah.
One that, and I guess my hint to you is right here is a sort of the famous identity that we use over and over again in algebra, all the way from algebra 1 through calculus through lots of things, is a squared minus b squared is a plus b times a minus b. This comes up all the time, right? And you can actually apply this to this denominator here. You can think of it as an a squared minus a b squared.
So,
So anyway, if you figured it out, there's another challenge in this one, which is the graph ends up being kind of strange.
Yeah.
Kind of a weird graph on this one. Just try your best on it. Try to figure it out. There's a new tech guy named Mike Nicosia. Is that Anna Bobana's like brother?
I didn't know she had a brother.
I don't know either.
I mean, she has a sister, but I don't know if she's.
Okay, so hopefully that hint was helpful. If not, sorry. I wanted it to be. The top is root x minus 3. Now, can I think of that x minus 9 is this form? Yeah, because x is kind of like root x squared in a way. Isn't it isn't. Technically, root x squared is the absolute value. Or no, actually, root x squared is a version of x where x has to be non-negative. Because you can't plug negatives into this.
Yeah.
Yep. Okay. So you can confirm that for yourself if you're like unclear at all. But yeah, if you multiply this out, root x times root x. Again, it's not technically the same as x, but as long as x is positive, they are the same. And in this function, wait, what's the domain of this function? Yeah, x has to be positive, but it also can't be 9. I'm sorry, I said that wrong. X has to be greater than or equal to 0. Sometimes I make the mistake of saying positive when I really mean not negative. Anyway, yes, Trey is 100% correct. These cancel out. And we have 1 over root x plus 3, which is a weird looking graph. If you thought, oh, I'll just take the 1 over root x function and shift it. That's not quite what's happening here. That you might have been thinking of if that radical had extended over the 3, then it would have been the 1 over root x function shifted left 3. But anyway, what you do to graph this is you say, well, let's say x was 0. That's the smallest value x is allowed to be, right? What's the y value? 1/3. And then just sort of, this is where you got to kind of use what we call the hand wavy argument. It's not that hand wavy, actually. Where you say, well, I mean, is this bottom getting any smaller? Just going to get bigger and bigger, isn't it? As x gets bigger. So what's going to happen to the y values? They're going to get smaller and smaller. And so our graph looks like this, with one exception. Yeah, don't forget, we're still not allowed. We're still not allowed to have 9 as an x value. What?
Some of my graphs look all terrible.
So an x is 9. By the way, where is the y value of the whole?
It's 1/6.
1/6. So the whole is at the coordinates 9, 1/6. Now my graph's not really the same, right? Like 9 is bigger than 1/3. I'm kind of changing my scale to make it to exaggerate the shape of the graph. All right. How do you guys feel about those? Okay. So let's do it this way. I'm going to cover the even odd functions because I mean they tie right in. It's really not any like really new stuff on top of what we already talked about. It's the same concepts. And then tomorrow we'll have a work day, so you can in class you'll have our class to just work on your assignment. So even and odd functions. Okay. I'll do a very quick overview Even and odd just refer to two different types of symmetry. And yeah, it involves end behavior for sure. There's a lot you can say about it, but in the most basic terms, here for anyone's taking notes out there, I'll give you a couple very simple examples. Here's an even function, y equals x squared, or y equals x to the fourth plus 3. That's also an even function. Or y equals 1 over x squared plus anything I want,
Uh-oh.
7.
Not the-
Or
I barely.
x squared over x squared plus 1. That's an even function. So the type of symmetry here is, I don't know, let's look at x to the fourth plus 3. It looks like this. And all it even means is that for every point A, B that lives on this graph, there's a corresponding point, his best buddy, at negative A, B. So in the simplest possible terms, it's on all these functions, pick any x value you want that's in the domain. Say this one, plug in 2. 2 would get you 19. Plug in negative 2, what do you get? The same number, 19. That's what an even function does, okay? Is you plug in a value, you plug in the opposite of that value, and you get the same y value. Okay, that's even. Odd is just, classic odd function is the x cubed function. You plug in 2, you get 8. Plug in negative 2, you get negative 8. So it's easy to come up with a bunch of examples to this one. This one you gotta be careful though. Can I just add, would this be odd? Plug in 2, you get 9. Plug in negative 2, you get negative 7. It's not the same.
Is the symmetry?
Yeah, so here's why. Look at, if I graph this, here, plug in 2, you get 8. Plug in negative 2, you get negative 8. How does he see his best friend? This guy has to look across the y-axis to see his best friend. This guy has to look
across the origin.
It's look through the origin. So if I shift this thing up by 1, it's not going to have that symmetry anymore. So like even functions, you can shift them up or down. It's not going to affect their symmetry. Odd functions, not the case. So some other examples might be things like, I don't know, about the fifth root function. Sure, that's even. Or sorry, that's odd. How about something like x over x squared plus 1? That's odd. Again, how do I know that's odd? Plug in 3, you'd get 3/10. Plug in negative 3, what would you get? Negative 3/10. Symmetry. Am I belaboring the point? Is that how do we feel about this? Is this confusing or is this like you're like, yeah?
Wait, who's, okay. The Osborne has a thing that, where if you're like beating a dead horse, you do this, because it's the dead horse.
I try to avoid that saying because
No,
one
you
time
should.
their horse had died.
Oh God.
They were really sad.
No, it's really sad. I'm just saying that that's what
unfortunate.
Osborne does, and I'm just like, it's a little interesting.
That's funny, yeah. Well, I try not to, but I don't know.
No,
Are we
good,
okay with that?
yes,
Does that make sense?
Yes. That just reminded me of that. I wasn't like saying anything. I just, yeah.
Okay. Now, this one will make my day if someone can remember this. Who is that? It's Humpty Dumpty. Yes. Very good. Humpty Dumpty.
Mr. Not-Ed.
Why is he Humpty Dumpty? Well, the first thing you would do when you say you see a function like this. This concept is especially important in calculus. We love symmetry. It's very helpful for us when analyzing something, a system. If I can know that this graph is just a symmetrical thing, well, that's nice to know. So how do I establish that early on? Well, let's say you don't know what the graph looks like. Okay, let's see. You plug in 4, you get 1/17. Plug in -4. Oh yeah, because you're squaring the x, turns it positive, you still get 1/17. That's pretty good evidence right there that it's an even function. Now that technically that has to be true for every pair of positive and negative x values. But
Oops.
that just one pair is usually a decent, is pretty good evidence. So anyway, y-intercept is at 0, 1. What's the end behavior? Yeah, so if all you have to do now is recognize that, okay, it starts at 0, 1 and it has to approach 0 on the right. Well, because of the symmetry, it must just do the exact same thing on the left. So on this problem, I've asked you to do the domain and the end behavior. So the domain is all reals, of course, because this denominator can never equal 0. And then the end behavior, approaching infinity as approaching 0, approaching negative infinity as approaching 0 as well. So yeah, these are pretty much all going to be, it should be hopefully fairly straightforward. Maybe let's do C. We'll do C as our last one we cover together. So C is the same function pretty much, except there's an x on top as well. So ask yourself right now, it's in your head, you picture it. What would that have to look like? What would that look like? A lot of similarities to the other one, right? How about, is the domain the same?
Yeah.
Is the end behavior the same? Yeah, because the bottom's a bigger degree than the top.
Oh, it's just that you can't have 0 on the horizontal.
Well, if you plug in 0 into this function, what comes out?
0.
The big difference, well, there's also the fact that this function is odd this time. So if I pick, I don't know, let's pick the same number I picked last time, 4.
Oh, you can have negatives.
If I plug in 4, I get 4/17. But if I plug in -4, this time I get -4/17.
Oh, this one just looks like a regular.
So the symmetry here is, it's now odd symmetry. And so this guy, this part of the graph, I found it kind of interesting that, I mean, could he be all squiggly up there? Sure, not really sure. One nice thing about calculus is that you can show why this thing only has one little hump. Establish that. There can only be one hump, and it can only go so high. And then on the left side, it's going to be symmetrical. So this is, of course, an odd function, whereas this one was even function. Very good. Thank you. So, yeah, anyway, this one has an interesting range. This one's range is 0 to 1, not including 0. This one's range is some negative value to some positive value, but it's not 1. Okay. It's too much excitement, It's just, let's end this thing here.
Exciting day.
Exciting day. And
To look out.